In this lecture, we conclude our introduction to the node voltage method for determining currents and voltages in circuits by presenting two examples that involve voltage sources that are not connected to the ground or reference node. Well, here's a circuit with two voltage sources, one current source, and three resistors. Now we can begin analyzing this circuit by selecting one of the nodes, and we'll select this bottom node as our reference node, or our ground node, and then we'll label the voltage relative to this ground at these other two extraordinary nodes, and I'll call this one V1 and this one V2. Now if we begin writing node voltage equations for the node with the voltage V1, for instance, we'll run into a problem when we try to define the current flowing through this 9-volt source. Now at first that might seem frustrating, but with a little thought we can see that the source provides a simple relationship between the node voltages V1 and V2. In particular, we can notice that V2 is V1 plus 9 volts. So if we write that relationship, so again, V2 is the voltage at this node is the voltage at this node plus 9, because there's a 9-volt voltage source between them. So now knowing one of these node voltages tells us the other. If we know the voltage here, V1, then V2 would be V1 plus 9. So in effect, there's only one independent node voltage, and the two nodes could be combined, and commonly are, into something that's called a supernode. So let me encircle these two. And so now, rather than thinking of a node as simply as a place where wires come together, we're thinking of it as a region where four wires enter. And so Kirchhoff's current law would tell us that if we look at all the current flowing into this region, that must be equal to all of the current flowing out of the region. So this is a generalization of Kirchhoff's current law to regions, closed regions within a circuit. Now the wires on the left, they connect to the node with a voltage labeled V1, and these two wires are actually connected to a node with a voltage labeled V2. But when we begin to write Kirchhoff's current law, we can choose either one of these. If, for instance, we write with respect to V1, any equation we write that uses this node voltage will replace that with V1 plus 9. So let's take a look at that. So the first equation I'll write is for the current flowing out in this direction. That would be V1 minus 2 over 2000. Now again, I'm suppressing the units, but we do know that the numerator has units of volts, the denominator has units of ohms, so this ratio has units of amps, and that is, we're writing expressions for the current. Now we have, in this direction, we have V1 minus 0 over 4000. Now out of this node, well, we have the current 1 milliamp flowing in, so we'll subtract 1 milliamp, and I'll write that as 1 over 1000. And then in this direction, we have V2 over 8000, but V2 is V1 plus 9, so I'll write it that way. And all of that is equal to 0. So now let's combine all the terms that multiply V1. So we have 1 over 2000 a 1 over 4,000, and a 1 over 8,000. So this, if we put everything over 8,000, then for this one we'd have to multiply by 4. For this we would multiply by 2, and this one by 1. So that'll give us a 4 plus 2 plus 1, or 7. So 7 over 8,000 times V1. So we have a negative 2 over 2,000, negative 1 over 1,000, and a 9 over 8,000. So if we put all of those over 8,000, we'll multiply by 4, so we'll have a negative 8 over 8,000, have another negative 8 over 8,000, and a positive 9 over 8,000. That'll leave us with a negative 7 over 8,000. If we take it to the other side, that will be 7 over 8,000. And that tells us then that V1 is equal to 1 volt. And then we can go back to this equation and find that V2 is V1 plus 9, or 10 volts. So that's a simple example of how we use a supernode when two nodes are connected by a voltage source, and then use the node voltage method to solve for one of the voltages, which in turn gives us the other through the relationship that ties them together with the voltage source. Well, here's a more complicated circuit with two independent voltage sources, one dependent voltage source, and one dependent current source. Now, the dependent voltage source has a voltage that's proportional to this voltage across this 1 kilo ohm resistor, and the dependent current source has a current that's proportional to the current through this 1 kilo ohm resistor. Now let's begin by assigning our reference node. Let's use this bottom node. And then we'll label the other nodes. Now I'll take this node at the top and give it a voltage relative to ground of V1. I'll make this voltage relative to ground V2. This one V3. This one V4. And this one V5. Next, I'll take a look at them and see if any of these can be simplified. Well, right away I notice that V2 is connected to ground through this 12 volt source. So relative to ground, this is a positive 12 volts. So I'll write that, and right away we've solved for V2. So that's 12 volts. Then if I look at V3, well, V3 relative to ground is twice Vx. But Vx, well, that's the voltage at V1 relative to V2, so I'll write that as V1 minus V2. So Vx is V1 minus V2, so I can write V3 as twice V1 minus, but V2 is 12, so that would be 24. And then let's see, do we see any others? Well, we're going to need this current, Ix, and that's related to V4, but V4 is connected to V1 through this 6 volt voltage source. So another expression we might have is that V4, and that's going to form a supernode. That'll be V1 plus 6, and then Ix, this current, well, that's V4 minus 0 over 1,000. So that's going to be V1 plus 6. V4 is V1 plus 6 over 1,000. So what we've done is we've gone through this circuit and tried to identify any places that we could simplify expressions for these voltages. So we notice that V2 is 12 volts, V3 is twice Vx, but Vx is V1 minus V2. We notice that V4 is V1 plus 6, and then Ix is V4 divided by 1000, but V4 is V1 plus 6. So there's our expressions that we may find very useful as we start to write the equations. Now, I mentioned earlier that V1 and V4, because they're connected by a voltage source, that forms a supernode. So let me just show you where that supernode is. I'm going to enclose it this way. So basically I'm going to draw a region around every wire that enters the node with the voltage V1 or V4. So that's going to be 1, 2, 3, 4, 5, 6. And 6 wires. This one, and this one all connect to V1, this one, and this one all connect to V4, but when we need a voltage to describe those, we'll call in this relationship that V4 is V1 plus 6. So let's write the equation for this supernode. Now the first current leaving this supernode is V1 minus V2 over 1000. Of course V2 is 12, so I'll write that as V1 minus 12 over 1000. Then we've got V1 minus V3, but V3 is 2V1 minus 24, so that's going to be V1 minus V3, so that'll be minus 2V1 plus 24, and that's divided by 1000 ohms. Then let's see, we've got V4 minus V3. V4 is V1 plus 6. And V3 is 2V1 minus a 24. So we subtract that. And that's all over 1000 ohms. Then we have this term, V4 minus 0 over 1000. Again, V4 is V1 plus 6, so we'll add in a V1 plus 6 over 1000. And then we got a V4 minus V5. So V4 is V1 plus 6. And then we'll subtract V5 to get this current, and that's divided by the resistance, which is 1000 ohms. And then finally we have this current leaving the node, so that'll be plus 2Ix, but Ix is V1 plus 6 over 1000. So we write this is 2 times V1 plus 6 over 1000. And set all of that equal to 0. Now the second equation would be a node V5. So the first expression, the first current leaving that would be this one perhaps, V5 minus V4. So that's V5 minus V4, but V4 is V1 plus 6. Over 1000. Then we've got this current, which is V5 minus 0 over 1000. And then minus 2Ix, since that enters the node. And Ix is V1 plus 6 over 1000. And set that equal to 0. Now, the first supernode equation has the unknown voltage V1 and the unknown voltage V5. The second supernode equation has the unknown voltage V1 and V5. So at this point, we have two equations and two unknowns. And if we simplify those, we should be able to reduce this to the following two equations with two unknowns. So if we group in the first equation all of the terms that multiply V1. So we have 1 over 1000, 1 minus 2, a 1, a minus 2, a 1, a 1, and a 2. We'll be left with 3. And then we take all the terms that multiply V5. And that should give us minus 1 over 1000 times V5. And then if we take all of the constant terms, group those together, move them to the other side, we'll have a negative 66 over 1000. And then if we simplify the second equation, group all the terms over that multiply V1, we'll get negative 3 over 1000. All the terms that multiply V2, we'll have 2 over 1000, or V5 rather. And then group all the constants, move them to the other side, and we'll have 18 over 1000. So now let me bring in a MATLAB window. And I'll type in an expression for that matrix G, which has 3 over 1000, negative 1 over 1000 in the first row, negative 3 over 1000, and 2 over 1000 in the second row. And then for I have negative 66 over 1000 in the first row and 18 over 1000 in the second row. And then V, which is the inverse of G times I, would tell me that V1 is negative 38 and V5 is negative 48. Now once I know V1 and V5, I can use these expressions. I can solve for V4, I can solve for V3, and I already know V2, so now that I know V1, V2, V3, V4, and V5, I should be able to find any current or any voltages in this circuit.